Okay, here we are back for more discussion of carboxylic acids and esters. So here in this second lecture, now that we've gotten the basic understanding of carboxylic acids and their nomenclature down, we're still going to continue to focus on carboxylic acids, but don't worry, the esters will be soon in our lectures. So the particular focus of this lecture will be on the properties of carboxylic acids. So we've looked at naming them, we've looked at how we get them, right? Oxidation generally of primary alcohols or aldehydes. And so now we're going to look at some properties of carboxylic acids. One of the most important properties of carboxylic acids has to do with the polarity of the carboxylic acid itself. Carboxylic acids are strongly polar, right? Because they have those two polar groups, the hydroxyl group and the carbonyl group. So those work together to form a very strongly polar end of a molecule. I say the end because, as we've already discussed, the carbon of the carboxylic acid has to be carbon 1 in a straight chain because it only has one way it can grow. So that's why it's a head group, and in particular it's a polar head group because it happens at the end of a molecule, and it's very, very polar because of the ability to undergo hydrogen bonding with that OH group of the carbonyl or the carboxyl group, and also hydrogen bond accepting abilities with that partially negative oxygen of the carbonyl. So that makes it incredibly polar and gives it very special properties in terms of the carboxylic acid functional group. As a result of that extreme polarity, we get very high boiling points for carboxylic acids, much higher than those of alcohols, ketones, and aldehydes of similar mass. In particular, you get high boiling points because the carboxylic acids can form dimers, where they are perfectly made to complement each other's hydrogen bonds between those two polar carboxyl groups. And we see here a picture of one of those dimers where we have two ethanoic acid or acetic acid molecules, as they're more commonly known. You see the carbonyl group of the acetic acid on the left is a hydrogen bond acceptor of the OH group on the right. And down below, the OH group of the left molecule is perfectly poised to be a hydrogen bond donor to the acceptor carbonyl oxygen of the molecule to the right. So they're perfectly made for this. They'll always be able to line up at the ends because, of course, the carboxyl groups happen at the end of each molecule. So there we see dimer formation, and that helps to explain these incredibly high boiling points for carboxylic acids. So if we take a particular example here, let's look at 3-carbon aldehyde, primary alcohol, and carboxylic acid. So if we look at propanal, its molar mass is 58, it's an aldehyde, and its boiling point is 49 degrees Celsius. For the corresponding alcohol, 1-propanol, we have a molar mass of 60. It's an alcohol, and as we said, the alcohols can hydrogen bond, so they do have higher boiling points than the aldehyde or ketone that would be roughly the same molar mass, and so we see that here with a 97 degree Celsius boiling point. But if we look at the ethanoic acid, which has that same molar mass of 60 grams per mole, now being a carboxylic acid, it has an even higher boiling point, over 20 degrees higher at 118 degrees Celsius. So very, very high for a quite small organic compound. So there we see, as we look at aldehydes, and aldehydes of course are even higher boiling than ketones. If we had the corresponding ketone, it would have even a lower boiling point for roughly a mass of 58 grams per mole. So there we have it, relatively low boiling point for the aldehyde or ketone, higher boiling point for the alcohol, but higher yet, incredibly high boiling point for the carboxylic acid due to that dimer formation. Now we've talked about the ability to form dimers with other molecules of themselves, but carboxylic acids can also form hydrogen bonds with water molecules, right? The image here shows that carboxylate group, carboxylic acid group, I should say, forming hydrogen bonds with no less than, what do we have, 5 water molecules here, but of course we've also got three-dimensionality to it, and the fact that those water molecules can hydrogen bond with others, but again, it gives you some indication that these carboxylic acids, at least the carboxylic acid group is quite loving of water, hydrophilic, right? If we have a small enough carbon chain, so say 1 to 4 carbon atoms, these carboxylic acids are very soluble in water. So methanoic acid, ethanoic acid, these things are quite soluble in water, essentially miscible with water for those really small carbon chains like the formic acid, or IUPAC name, of course, methanoic acid, or acetic acid, known by IUPAC name as ethanoic acid. So really small ones like the ethanoic acid we see here are quite soluble, essentially miscible with water. Here in table 16.2, we get the boiling points, solubilities, and acid dissociation constants for some small carboxylic acids. So the methanoic acid's the smallest possible carboxylic acid. Its boiling point is 101 degrees Celsius, so just over the boiling point of water itself, and it's very soluble in water. The acid dissociation constant gives an idea of the strength of the acid, and so this is 1.8 times 10 to the minus 4. This is a fairly strong organic acid. If we move on to ethanoic acid, again, just a 1 carbon larger, boiling point goes up to 118 degrees Celsius. It remains very soluble in water, and its acid dissociation constant's a little smaller at 1.8 times 10 to the minus 5, so an order of magnitude smaller acid dissociation constant. If we go up to propanoic acid or propionic acid, depending on if we're talking about IUPAC or common name, notice the boiling point goes up a fair deal because we're getting larger in terms of molecular weight. We remain soluble in water, and our acidity is a little smaller at 1.3 times 10 to the minus 5. Next, we see the butanoic acid, the largest of the soluble carboxylic acids, water soluble anyway. Nice high boiling point, 164 degrees Celsius, and again, a slightly smaller acid dissociation constant. It's actually larger than the propanoic acid, but smaller than the ethanoic acid. So big change between methanoic and ethanoic, right, an order of 10, but then relatively small changes between ethanoic, propanoic, and butanoic acids. If we continue our examination up a couple more carbon lengths, we see that the pentanoic acid, the boiling point continues to increase, the solubility in water starts to go down a little bit, acid dissociation constant right around the same as the previous example. For hexanoic acid, now we've gone to a high boiling point above 200 Celsius here, but we've also decreased notably in water solubility. So now we're only slightly soluble because we have a significant nonpolar hydrophobic end to the tail of the molecule. We still have that nice polar head group, but the tail is not very water loving. And then the acid dissociation constant drops just a small bit here. And then finally, if we look at benzoic acid, which is, again, similar in molar mass to hexanoic acid, we see that it has a very high boiling point at 250 degrees Celsius, and it's only slightly soluble in water, but it has a higher acid dissociation constant because of that phenyl group, the benzene ring. The aromatic helps to give it a fairly high acid dissociation constant compared to everybody but methanoic acid. So there we have some ranks. Again, boiling point continued to increase along with molecular mass, but water solubility went down, and acid dissociation sort of was spotty at best. Okay, so although it was the least predictable of all those properties on those tables, let's take a look at the acidity of carboxylic acids. So carboxylic acids are weak acids, and they ionize in water to produce carboxylate ions and hydronium ions, according to the reaction we see below, specifically for ethanoic acid, or as it's commonly known, acetic acid. So a molecule of acetic acid or ethanoic acid interacts with a water molecule in an equilibrium process, which is greatly favoring the left. Actually, most of it stays as the neutral ethanoic acid, but some small amount will dissociate. The proton from the carboxylate group will be donated to the water to form hydronium ion, and there by leaving behind an ethanoate or acetate ion. So it's just same sort of thing we explored back last semester in Gen Chem GOB, General Organic Biochem 1, where we focused on the general chemistry. We have an acid plus water in equilibrium with the acid anion and hydronium ion. Now, because they're weak acids, carboxylic acids have small acid dissociation constants, which means they exist mostly as those neutral molecules and only a few ions in aqueous solution. Of course, if we wanted to help them along, we could force those protons off by going into basic solution, but if we want to keep them just as neutral water as the water source, then we're going to get only slightly acidic solutions because we have very little tendency to go in the forward direction due to those small acid dissociation constants for these weak organic acids. I just mentioned previously the idea of helping these along to bring that proton off. So if we neutralize the carboxylic acids, we can make carboxylic acid salts. So they're the products of neutralization of a carboxylic acid with a strong base. So if we see methanoic acid or formic acid, as it's more commonly called, interacting with a strong base like sodium hydroxide, we form sodium methanoate or sodium formate, depending on if you're using IUPAC or common naming schemes, plus water. If we did the same sort of reaction with benzoic acid and another strong base like potassium hydroxide, we can make potassium benzoate and water in that example. You've probably seen potassium benzoate in particular, probably not too much sodium methanoate, but potassium benzoate is a common preservative and flavor enhancer used in prepared foods. The other benefit, we didn't talk about it because it's not so apparent for acids you don't encounter much, like methanoic acid. Acetic acid or ethanoic acid, I'm sure you've smelled. It has that characteristic sour vinegar odor. If we went to butyric acid, it has sort of a vomit smell to it. These carboxylic acids are strong, unpleasant odor compounds, and cleaners tend to be basic, and that'll help to deprotonate the carboxylic acid. Once you form the carboxylic acid salt, you've eliminated the smell. So something very unpleasant like butyric acid, if you wipe it up with some base, you make essentially an odorless product, the carboxylic acid salt. So not only is this an interesting chemistry example, but it's got that real life practical cleanup aspect. If you ever notice unpleasant smells, there's goat odors due to carboxylic acids largely. If you want to get rid of odors, make sure you wipe up that vomit with some base and it'll take care of that smell very, very quickly. Okay, on that pleasant note, let's go ahead and have our last learning check here and close our properties of carboxylic acids lecture. So in this learning check, you're asked to write the equation for the reaction of propanoic acid with each of the following. So first with water acting as a weak acid, and second with a strong base like potassium hydroxide to get that carboxylate salt. So go ahead, stop the video here while you write those reactions, and then start it back up to check your work. Good luck. Okay, so here's our solution. Propanoic acid, that's the IUPAC name for a 3-carbon straight chain carboxylic acid. And there we have it. In the first case, we were told to have it react with water, so good old H2O is our co-reactant. It's an equilibrium process there because it's a weak acid, so we show the double arrows, and then we get the propanoate ion and the hydronium ion. For B, if we're going to have a strong base like potassium hydroxide, now we fully deprotonate to make the carboxylate salt, the potassium propanoate plus neutral water. So there we have those reactions equations. Hopefully they're exactly what you came up with. If not, hopefully you understand now why you may have gone wrong in writing one of those or both of those. If that's not the case, if you didn't get it quite right and you're not quite sure what went wrong, then certainly please try some additional practice problems and then reach out to me for help if it's still not making sense. Of course, we hope everything's making perfect sense, and I look forward to seeing you in the next section of Chapter 16.